This lecture is about IP addressing, and we are going to talk about IP addressing related to routing. Very useful to understand how the routing tables are populated. So I'm going to share the big screen now. The agenda is to talk about IP addressing. We'll talk about the notation, prefixes, subnets, and finally longest prefix matching. We already understand what prefixes are. It's the earlier portion of IP addresses. And this understanding of IP addressing will lead to the understanding of border gateway protocol, which is the protocol which connects different service provider networks. And it is used for internet scale routing. So in order to understand the population of routing tables, we already know that every host must announce its own IP address. So a host that wants to be reached on the internet, if I want to be reached on the internet, I must announce my presence by announcing my own IP addresses. Okay. However, will I announce my own IP address and everyone will do the same? Will this IP address get into the routing table of the routers? There are 4 billion IP addresses and much more with IPv6. For IPv4, we have 4 billion IP addresses. It is not possible to have all of those 4 billion IP addresses in the routing tables. And the reason that we do not want to have so many IP addresses in the routing table is because when a packet is received by a router, it must match the destination IP address in that packet with the entries in the table. And if there are 4 billion entries in the table, it will take a lifetime to match the destination IP address with the entries in the table. We need an instant lookup in the routing table. For example, if we have 100 byte packets and the link is running at 40 gigabit per second, you have about 20 nanoseconds to make a decision on the fate of the packet because the next packet is in line and it will be waiting in 20 nanoseconds. So you have very little time to decide where this packet that you have just received should be forwarded to. So that means there is very, very little time to consult the routing table and match the destination IP address into this routing table. A routing table with 4 billion IP addresses would not be able to provide this kind of luxury. Yeah. Now, considering that it is not scalable to put IP addresses in the routing table, what is the solution? What is the solution? So we do not put the IP addresses in the routing table. Instead, we put prefixes in the routing tables. And one prefix, as we understand, is the first several bits of the IP addresses, and it represents a group of IP addresses. Now, who will put these prefixes into the routing table? We know that every host has just one single IP address, but many of these hosts might be connected to a router, directly connected to a router or indirectly connected to a router. So a router which knows how to access a group of IP addresses, which are represented by a single prefix, that router would be responsible for announcing the prefix. So a prefix represents a group of contiguous IP addresses such that they can be represented by a single prefix. And who will announce this prefix? A router will announce the prefix. And which router will announce the prefix? Any router which knows how to reach any of those IP addresses represented by that prefix or covered by that prefix. To consider an example, let's say we have a routing table with the following two entries. So we have an IP address, which is shown in the dotted decimal format, and we'll talk about the dotted decimal format again, and also shown in the binary. Okay? And then there is another IP address in the same routing table. So we are showing only two of these IP addresses. What is a possible prefix for this particular example? So if you look at the first several bits of both of these IP addresses, you will see the similarity between the bits. Okay, so first 8 bits of this IP address and first 8 bits of this IP address, they are common. The next 8 bits are also common. Okay, and you can continue this. So what is a valid possible shared prefix in this example? The 21-bit prefix is the longest that is common between these two IP addresses. A shorter prefix would also be common, of course, but the longest one that is common between these two IP addresses is a 21-bit prefix, which is shown here. Okay. So this 21-bit prefix contains or covers 2 to the power 11 different IP addresses, 2 of which are given here. But there are many other IP addresses which are covered by this one single prefix. This one single prefix is a 21-bit prefix. It covers 2 to the power 11 IP addresses. Okay. So all of these 2 to the power 11 IP addresses are covered or aggregated in this 21-bit prefix. A router which announces this particular prefix, must know how to deliver to all of these folks. Okay. If a router knows how to reach these two guys, this router is not allowed to announce a prefix like this. Because if you announce a prefix like this announcement of this prefix indicates that this router is able to reach all the possible IP addresses covered by this particular prefix. Okay, so for the above example, any prefix which is shorter than 21-bit would also be a valid prefix, and a router announcing that shorter prefix would need to make sure that it is able to reach all of those IP addresses. Okay, so shorter prefixes, as we said, they cover or aggregate more IP addresses. A router announcing a shorter prefix would be responsible for accessing all of those IP addresses which are covered by the prefix which is announced by that router. Okay. How do we represent the IP addresses and prefixes? So IP address is represented in the dotted decimal format like this, or the binary format like this. This is a 32-bit number, IPv4 addresses. There are also IPv6 addresses, but we are only going to focus on IPv4 addresses for now. And this is called the dotted decimal notation, dotted decimal notation or dotted quad notation. Okay? 4 numbers written with dots in between. Okay? If you look at this IP address in the binary format, it would have a network part which is determined by what prefix covers or represents this particular IP address. Okay, and it will also have a host part which will indicate the variable part in this group of IP addresses, which are all covered by this one single network part, which is the prefix. So this network part represents a prefix which represents all the IP addresses which are covered by this prefix, where the yellow portion, which is the host part, could be anything from all zeros to all ones. Okay, so this would be 11 bits here. So 2 to the power 11 different IP addresses will be covered by this one single 21-bit prefix. 21-bit prefix. So the IP address itself would have this network part and the host part concatenated together. And this would be a 32-bit number. The prefix part would be the network part would be the first several bits, and the host part would be the last several bits. How many bits in the host parts and how many bits in the network part? It is dependent upon what is the length of the prefix and how many IP addresses do you want to cover in that one particular prefix. And the prefix notation for this particular example is that this is 203.108.88.0/21. /21 means that the length of the prefix is 21 bits. So this prefix has a length of 21 bits, which means that this particular prefix is covering 2 to the power 32 minus 21, which is 2 to the power 11 hosts. So last 11 bits are set for the host part, and those would be all zeros to all ones. Okay. And as far as the network part is concerned, the network part is the first several bits of this IP address, and the rest of the part host part would be considered as 0. So if you convert this particular number into the equivalent decimal format, you will see that this is 203 and then 108 and then 88 and then the final 8 bits would be 0. Okay. So all the IP addresses covered by this prefix would be reachable by the same router. A router announcing this prefix should be responsible, should know how to reach all of those 2 to the power 11 IP addresses. Now, how do you get a subnet from an IP address? Just by looking at an IP address, which is just a 32-bit number, you cannot tell whether this is a what is the length of the subnet part or the network part, and what is the length of the host part. By the way, the subnet part and the network part is one and the same thing. So can you tell the specific prefix by looking at an IP address? The answer is no, until you know the size of the subnet. Once you know the size of the subnet, then you will be able to tell the network portion or the subnet portion of the IP address. So let's consider this IP address, which is a 32-bit number. Just by looking at this IP address, I cannot tell what is the length of the subnet portion or the network portion, and what is the length of the host portion. However, if we know the length of the network portion or the host portion, then obviously I can tell that what is the prefix which covers this IP address and many other IP addresses which belong to the same block. Okay, so a prefix which covers this IP address, a prefix which covers this IP address, and many other IP addresses like this one, with the same network portion is shown here. This prefix is shown here. And there is another terminology which is used, which is called the subnet mask, which is obtained by using all ones for the network part, all ones for the network part, and all zeros for the host part. And you can see that this is obtained, this subnet mask. From the subnet mask, we can obtain the prefix by taking the binary AND operator of the subnet mask with the IP address. So there is a group of IP addresses which is represented by this prefix. You take any of those IP address and take a bitwise AND or binary AND with the subnet mask, you will get exactly the same answer. Exactly the same answer. Why? Because the last several bits, the host part of the subnet mask, are all zeros. By the way, this IP address and the subnet mask, they are both configured in your network setting, which is often obtained by a DHCP servers by your machine when it is booted up. The sender will determine if the destination is in the local host if the subnet portion is the same as yours. So for example, if there is a sender who knows its own subnet part, who knows its own subnet mask, so it will know its subnet mask, it will know its subnet part. If the subnet part of the destination is same as the subnet part of the source, which is obviously known to the source, then the source will determine that the destination is in the same local network. Otherwise, it will be in a different local network, and the delivery to a different network must be done through a router. Okay. So all the local hosts which have the same subnet part, are reachable to each other without the use of the router. And if you want to go across to another local network, you must use a router to reach another local network. So what is aggregation? A router will aggregate the IP addresses of all the hosts which are connected to itself, if it is possible to do so. Most often it is possible to do so because the IP addresses are hierarchically, geographically distributed. That means all the IP addresses in the local vicinity will have addresses which are in the numerical vicinity of each other, such that they can be aggregated with each other. Once a router aggregates an IP address, it will announce the prefix by saying that I will take care of this prefix. But that means is that I will take care of all the hosts. I will be responsible to deliver a packet for all the hosts which are represented by this particular prefix. And this prefix will be announced by this particular router. and will be populated into the routing tables of other routers. So those other routers, when they see an IP address whose first several bits match this particular prefix, they will forward that packet towards this router, and this router will be, as promised, responsible for delivery of the packet to the particular hosts. So an upstream router may further aggregate. As you can see that prefixes themselves can be aggregated with each other, and they might advertise a shorter prefix to more hosts, representing more hosts. In practice, a router in the school building, School of Science and Engineering building, will announce a simple prefix, a long prefix, which will represent all the hosts within the SSE building. To whom this will be announced? This will be announced to the university router, and the university router will announce to routers to the outside world. Um, the the number of the prefixes announced by the LUMS router to the outside world would contain or would cover all the IP addresses which are part of the university. Okay. And what will the PTCL router in Lahore announce? It will announce all the prefixes in Lahore, maybe can all aggregated together to a PTCL router in Karachi, which will be announced, which will be announcing prefixes by aggregation out of Pakistan. And this will be announced to service providers which are providing services to the PTCL, through which the rest of the country is getting the service. And examples of those are Singapore Telecom, Singtel, and PCCW. And Singapore Telecom and PCCW, they would be announcing those prefixes further into the internet so that these prefixes propagate throughout the internet, and anywhere on the internet is able to reach any host within LUMS, any host within PTCL's network, any host within PTCL's network in Lahore, any host within LUMS, any host within the School of Science and Engineering building. Okay. So a pictorial way of looking at the prefix announcement allocation is that by considering this entire IP space where the leaves of this tree type of a structure, they represent the IP addresses. So the leftmost is the smallest IP address and the rightmost is the largest IP address, all zeros to all ones. And all the IP addresses, 2 power 32 IP addresses, are covered within this tree. A small portion of this tree will be allocated to a particular organization. You can see that as you move up the tree, as you move up the tree, you will have shorter prefixes and they will be covering more and more IP addresses. The smallest prefix, which is the star here, will cover the entire IP space, will cover the entire IP space. A prefix starting with 0 only, just 1-bit prefix, will cover half of the IP space. Similarly, a prefix starting with 1 only will cover the rest of the half of the IP space. So within this IP space, let's say the School of Science and Engineering SSE building has gotten the IP addresses, which is represented by this number here. Okay, so this represents a small IP space in the entire 2 to the power 32 IP space, and this can be represented by a single prefix. Okay, this is called the SSE prefix. SSE prefix will be announced to the LUMS prefix, and the LUMS prefix would be covering a larger number of IP addresses, some in the SSE building, some in some other buildings, and LUMS prefix will be announced to the upstream router, which is PTCL Lahore. So PTCL Lahore will have even more IP addresses, and PTCL PK will have even more IP addresses, and so on and so forth until the entire IP space is covered. So where does the SSE will get its IP addresses from? SSE will get its IP addresses from a DHCP server, and that DHCP server will know that I have to allocate the IP addresses to the SSE host within this particular range, And this will be obtained from the LUMS pool, which will get from the PTCL Lahore's pool, which will get from the pool of which is allocated to PTCL, which will get it from the Singapore Telecom or PCCW's pool, or even from directly from the numbering authorities such as APNIC and ICANN, we can also get the IP addresses directly from those instead of getting those from our service provider. Okay. So let me just talk about the IP addresses classes that are used for routing. The original design, which is completely obsolete now, I'm just going to very quickly talk about it. And the way that these IP address classes are different are the length of the subnet portion or the network portion and the host portion. In the original design, the network portion is 8 bits fixed, and the rest of the 24 bits are for the host portion. Okay. So there were only 256, which is 2 to the power 8. 256 prefixes were allowed, each with 2 to the power 24 hosts. So the assumption was that there will be only 256 organizations maximum in the world, and each organization will get 2 to the power 24 hosts. That was a very bad assumption. Obviously, we have thousands and hundreds of thousands of organizations who are looking to get smaller portions of smaller blocks of IP addresses. Nobody needs 2 to the power 24 IP addresses. Even a few IP addresses might be sufficient. Okay, so a prefix here represents a network with a very few networks. So very few networks were available to us, and that is why this design was obsoleted very quickly. And then we went to multi-class addressing. Multi-class addressing is also obsolete now, and I will talk about the reasons for the obsolete why multi-class addressing got obsolete as well. First of all, we have class A IP addresses in which the first 8 bits are the network portion, represent the network portion or the subnet portion, and the last 24 bits represent the host portion. This is similar to the original design, but what we have done here is that we start all the class A IP addresses with a bit 0, which means the IP addresses which start with 1 do not fall in class A. Okay, but the IP addresses which start with 0 fall in class A. That means 50% of the entire IP space falls in class A. Okay, and then we have class B IP addresses in which the first 16 bits represent the network portion and the last 16 bits for the host portion. And the starting bits for each IP address in class B is 1, 0, and many bits after that, up to 32. Similarly, we have class C, which have 24 bits for the network portion and 8 bits for the host portion. And the starting bits for all the class C IP addresses are 1, 1, 0, and anything after that, up to 32 bits. Okay. So classful or multi-class addressing was a bit better than the original obsoleted addressing, but this also got obsoleted, and we'll go into the reasons. Before that, let's consider how many IP addresses do we have and how many address organizations that I can accommodate with class A IP addresses. With class A IP addresses, they have this /8 kind of the IP addresses, which means the first 8 bits, they represent the subnet or network portion, and the last 24 bits, they represent the host portion. Okay, so that means that we only have 128 networks, 128 networks which are covered, which are represented by the first 8 bits of the IP addresses. The first bit must be 0. So that means we are left with these 7 bits here, and 2 to the power 7 gives 128. So we have 128 different organizations which can be given class A IP addresses. For each class A IP addresses, the host portion is 32 minus 8, which is 24 bits. So that means 2 to the power 24, which is about 16 million addresses, which means that each of these 128 organizations can get 16 million IP addresses. No organization needs 16 million IP addresses. That's why this is also obsoleted. MIT used to have, I'm not sure if they still have this one class A IP address. IBM used to have a class A IP address. Stanford used to have a class A IP address. Stanford gave up the class A IP address. Now they have class B IP addresses. Well, the classes are gone anyway. But the address allocation has been with the class A and class B from the early days. Okay? So half of the entire IP address space is consumed with class A IP addresses. Then for class B IP addresses, the starting bits are 1, 0. The first 16 bits are the subnet part, and the last 16 bits are the host parts. So that means we have 2 to the power 2 to the power 14, which is the 14 bits here, instead by removing this 1 0 from the 16 bits. So it's not 2 to the power 16. The first 2 bits for each class B addresses are fixed at 1 0, and the rest of the 14 bits are anything, don't care. So 2 to the power 14 is 16,000 networks, and each of those networks will have a host portion which is 16 bits long. So this would be 2 to the power 16, 65,000 IP addresses approximately. So this also represents about 25% of the entire IP address space. So 75% of the entire IP address space is gone in class A and class B only. Then we have class C IP addresses, which the starting 3 bits for all the class C IP addresses are 110. There are 2 million different networks. That means so many organizations I can accommodate, which is great. When multi-class addressing came about, people were very happy that they can accommodate many more organizations, and each organization will get 256 IP addresses, which is host portion, the 8-bit host portion um, in the class C IP addresses. The first 24 bits are the network portion or the subnet portion. Okay. So 1/8 of the entire IP address space is consumed by class C IP addresses. So where did the 1/8 of the remaining space go? There are other 2 classes of the IP addresses, class D and E, which are reserved for special purposes. What are the drawbacks of this class full addressing, which obsoleted the original addressing, and it worked well for some years, but it became obsolete because there were some drawbacks here as well. Um, so some of the drawbacks is that it only comes in 3 sizes. Okay? You have class A, which are very large blocks, or class B, which are mid-sized blocks, but there are very few of class B blocks available. And then we have class C blocks, which are many blocks are available, and each block can have just 256 IP addresses. There are many organizations which require more than 256 IP addresses. So what would they do? They will obviously try to get a class B IP address, but that might be a wasteful for them, because class B allows 65,000 addresses. So an organization which requires more than 256 addresses cannot be accommodated in class C, would want to get a class B. And this would be a wastage because there are only 16,000 class B blocks available to us. Okay. So, so the drawbacks of this class full addressing, which is also now obsoleted, is because there is wasted address space. If I don't fit in class C, I would want to get class B, and even though this is too much for me. So in particular, we have depletion of class B. There are only 16,000 different class B blocks. Any network with more than 256 hosts will need a block of class B. If you don't give a class B, then they would probably want multiple class C addresses. And once you get this multiple class C addresses, they may or may not be aggregatable with each other. If they are not aggregatable with each other, they will be announced as separate prefixes into the internet, making the internet routing tables very large. Okay. So addressing which is in use today is classless interdomain routing. It's called classless interdomain routing. It is not limited to just 3 classes of IP addresses, which had 8 bits, 16 bits, and 24 bits as the subnet part. Classless internet domain routing CIDR says that you can have a subnet portion which can be any number of bits. It can be 16 bits, it can be 17 bits, it can be 19 bits, it can be 23 bits. And it is very common to have subnets which are even longer than 24 bits. Okay? So there is a variable length subnet or network part. How does the provider get this subnet part? That means the group of IP address. It will get it from its upstream provider. The upstream provider will provide that, or it can also get it directly from the numbering bodies. The remaining bits are for the hosts to choose from uniquely. But the host, they are not going to choose it themselves unless you statically configure the IP addresses. Normally, you will get the IP address from a DHCP server, and DHCP server will know that this particular host in a particular location should get this IP address so that it can be aggregated with other similar kind of IP addresses. So the routing challenge here is that routing tables, they contain prefixes, but routers, they only see the destination IP addresses. If you recall the IP address block structure, it has the 32-bit source IP address, which is not used here. We use the 32-bit destination IP address. There is no information about prefix here. It's just this 32-bit number. So how do we use these prefixes in the routing tables to route these 32-bit IP addresses which are representing the destination? How will the lookup work? Can you just match the prefix? Well, the answer is not so simple. One might say that there are prefixes in the table, so you can just match the IP address into the prefix. However, there will be situations where you will have multiple prefixes matching the same IP address. Okay, and we will consider an example for that. Okay, before we consider that example, let me just go to longest prefix matching, which tells you that what happens when an IP address matches multiple prefixes into the table. So let's say you have a table like this, and as you can see that this prefix here, which is going to link interface 1, and this prefix here, they are prefixes of the third one is the prefix of the second guy. So this is the third guy, this is the second guy, this is the first guy. The third guy is a prefix of the second guy. So any IP address which matches the third guy may not match the second guy, but any IP address which matches the second guy, which matches here, will also match here. Which one will you choose? So we will use the longest matching prefix paradigm. Okay, let me give you an example. So let's say you have this IP addresses here. These IP addresses will go to which interface? If you look at the first IP address here, this first IP address matches the first entry and it will go to link interface number 0. If you look at the second entry, if you look at the second IP address, this matches the third entry as well as the second entry. So which interface would it go to? Well, it would go to the one where you have the longest matching prefix, which is this one. So it will be directed towards link interface number 1. To give an example why longest prefix matching is needed, let's consider this simple example of 8 organizations. This is organization number 0 up to organization number 7, which are all serviced by a single IP ISP, which is fly-by-night ISP. So this ISP aggregates the prefixes of each of these organizations into a single prefix. And you can verify this, that all of these 8/23 prefixes, they aggregate into this nicely aggregate into this /20 prefix. See, this /20 represents 2 to the power 12 IP addresses. Each of these /23 represents 2 to the power 9 IP addresses. Okay, and 8 organization into 2 to the power 9 IP addresses. This will give you 2 to the power 12 IP addresses, which is announced by this fly-by-night ISP into the internet. There is another ISPs RS, which is announcing a prefix for some other organizations that we are not worried about for now. Okay, now eight organizations are serviced by this one single ISP, and this is called the hierarchical addressing, where these addresses are nicely aggregated into a single prefix, That may not always be the case, but in this particular example, it is the case. Okay? Now, let's assume that this organization 1 also wants to get service because it wants reliability. Sometimes it happens that fly-by-night ISP fails. So organization 1, which is running some mission critical tasks, may be in need of a service from another different ISP. Just like the university has services from multiple ISPs. If one fails, it fails over to the other one. Okay. So this organization wants multi-homing. So it gets service from these two different service providers. However, it would prefer that the new ISP, which is ISPs RS, should be preferred over this fly-by-night ISP. So that means the primary traffic for this organization one should come from ISPs RS instead of fly-by-night ISP, unless the ISPs RS fails. If it fails, then the traffic should be routed by flight-by-night ISP. Okay. So, and the traffic is coming from the internet to organization one. So that means the information about organization one should be somewhere within these routing tables. So what that means is that this ISP must also announce the prefix for organization number one, must also announce the prefix for this organization one. So it will add this prefix 223.18.0/23 into its announcements, and this prefix will also be announced into the internet. Now the routers in the internet will have two entries to reach organization one. So routing tables out there will now have two valid prefixes to reach organization one. Which one will they choose? So this one is a /23, this one is a /20, and they will use the longest matching prefix. So they will go through ISPs RS. And the traffic will be routed by this dark blue arrow from the internet to organization one under normal conditions. Okay. If ISPs RS fails, then the traffic will be routed through fly-by-night ISP. Okay. What if organization one wanted to prefer fly-by-night ISP to get the traffic, and if fly-by-night ISP fails, it should get the service from ISPs RS. In that case, what should organization one do and what should fly-by-night ISP do? I will let you guys think about it. And if there are any questions, you can ask. Okay. So here is an example for forwarding with obsolete addressing. So if you look at these IP addresses, let's say there is a router here, which has a table, which is given by this, receives an IP address, where receives a packet with a destination IP address, which is given by this. If you look at the first 8 bits here, this represents 201. The next bit and next 8 bits are can also be converted into the respective decimal notations. Okay, so with obsoleted original routing, in which the first 8 bits are for the network part, you will look only at the first 8 bits, which represent 201. So this will match the routing table entry, which is given by this, and it's going to link to. So this packet, which contains this destination IP address, will be forwarded towards link number 2. Okay. Next, we consider the multi-class addressing, which is also obsoleted. The same packet is received with the same IP address. And if you look at this IP address, this IP address is slightly different from the previous example, actually. So this was 201, and this IP address was 201, and this IP address is 200. Okay. So which entry this packet will be matched to and will be forwarded to? Will it be forwarded to link 1 or link 2 or link 3? So this, if you look at this IP address, this belongs to the class C IP address, which is 110. Why? Because the first 3 bits are 110, and every class C IP address will have a 110 type of starting bits. Okay, so this packet will be forwarded towards link 3. Okay, now let's consider an example of CIDR, which is the practice these days, and the forwarding of this IP address, in which the first 8 bits, they represent 201, and then we have the next 8 bits, they represent 143, and then we have 5, and then we have whatever number is this. Okay. If you look at this IP address, we do not have any fixed length of prefixes. So instead of writing these IP addresses into the table, I will have the length of the prefixes included into the table. Now, this particular IP address matches all of these 3 entries. You can verify it at home. Which And which link this packet will be forwarded to? Well, this link will be forwarded to that entry which has the longest matching prefix, and the longest matching prefix is out of 21, 22, and 24, it's 24. So this packet will also be forwarded to link number 3.